So this next section is going to be on a new type of integral called the flux integral. So these are going to occur over surfaces in 3 space. But this short flip class video isn't really going to talk about the integrals themselves. We're just going to talk about how to parameterize surfaces, because that's going to be very important for actually being able to evaluate flux integrals. So we won't actually be doing any integrals in this video. But let's start by recalling how we parameterized things when we had one dimension. So when we were trying to evaluate line integrals, so integrals of a vector field over some curve in 3 space, we often parameterized the curve, and we used a vector function to do this. So we had like r of t is equal to x of ti plus y of tj plus z of tk, and then we let our t vary between some interval from a to b. And so this is how we were evaluating line integrals in many cases. So it's going to be the same type of thing when we want to do surfaces. If I want to integrate a vector field over a surface, I'm going to want to figure out how to parameterize that surface to make it something I can actually integrate. So let's introduce these. So like as I said, we want to be able to do the same thing for a surface S. We spent all of this time figuring out how to do integrals in 2 variables with rectangular and polar coordinates. We're going to put that to use when we parameterize the surfaces. So just how we were able to take a line integral, and when we parameterized it, it became just a regular Calc 2 or Calc 1 integral over an interval. When we parameterize our surfaces, it's going to take a surface in 3 space, and the integral is going to become just an integral over rectangular or polar coordinates in the plane. So since a surface has 2 dimensions, it's going to require 2 variables. We usually denote these as u and v. So what we're going to want is a vector valued function again, but in this case our vector valued function inputs 2 variables u and v, and it still outputs a vector, but now our output functions x of uv, y of uv, and z of uv, those each input 2 variables as well. And so we're going to have some region R inside the plane that will give all of the points of our surface S. And just like in parameterizing curves, there's no recipe for doing this. It's going to take practice, and the more practice we have, the better we'll get at it. And so the best thing to do is just to go through a few examples here and get kind of an idea of what's going on and how we might parameterize some surfaces. Let's go ahead and do that. So here's our first surface. So this is just a flat disk, but it's raised up. So this is at height z equals 2 for everything. And then I want the whole disk there. So I don't want just a circle. I want all the circles inside the main circle. So I want x squared plus y squared, and we want that less than or equal to 4. So you can remember x squared plus y squared is the square of the radius. So we're asking really for all of the circles of radius less than or equal to 2 at a height up of 2. And so we want to parameterize this surface. So the first thing we can tell is, since this has a constant height of z equals 2 for everything, I want that function z of uv to just be equal to 2. That's not going to change at all depending upon where I'm at. It should always be equal to 2. Now what we want to do is we want to say, okay, for the rest of this now it's at height 2, but I've got to get all of these points on this surface. And the way we can think of this is you can kind of see all of these circles here. I want to take and start with this point in the center, and then I want to work all of these circles into my parameterization. So we know if we wanted to just parameterize a circle of radius a, we could parameterize that as a cosine ti plus a sine tj, and we would let our t go between 0 and 2 pi. So we want to do that same thing, but now we don't want to only let the angle change, we want to also let the radius change to make sure we get all of those different circles to fill out the disk. So what we could do is, for the x and y values, we let those be u cosine v and u sine v. So think of that u there, that's our radius of the circle, and that's changing. So my u goes between 0 and 2 to get all of the circles between radius 0 and 2, and my v goes between 0 and 2 pi to get all of the possible angles. And of course we already said the z value is going to be 2. So that gives me my whole, the parameterization of the entire disk there. And you could also think of this, what would this look like? Well, this is just taking the disk in the plane and kind of moving it up. So it's just pointing it up everywhere. So note this is our region in in the plane here. So we're just taking, it's not exactly the circle because we didn't just go straight up, we're going out in terms of these. U's go between 0 and 2, and v goes between 0 and 2 pi because we used polar coordinates. And so it looks something like this. So each value is going to have an arrow pointing up to a point on the disk there. And that's how we would parameterize that surface. So it's almost a little harder there because of it being just moving something up to a flat disk. The easier ones are the ones that we're going to do next, which is if I have a surface just given by some function z equals f of xy. And so we saw when we were parameterizing curves, the easiest ones to do were just curves that were given by a function. And similarly here, the easiest ones to do are surfaces that are just given by a function. So in this case, we can just parameterize this as take u to be x, v to be y, and then my z value is just going to be f of uv. And so that's the easiest possible situation to be in, and it will be that case fairly often for us. Finally, let's do one more example, and obviously we'll do lots more examples when we're doing flux integrals. But let's look at this cylinder here. So in this case, I have the x and y values are always the circle x squared plus y squared equals 4. So this is a hollow cylinder. There's nothing inside of it. Then I'm going to let my z values go between -3 and 3. So you can kind of see what we need is for each value of z, we need to have a circle there. And it has to be a circle of radius 2 for every value of z. So what we're really wanting to do is parameterize a circle of radius 2 in the plane, and then kind of move that up and down from z equals -3 up to z equals 3. So we just saw 2 slides ago how to parameterize a circle of radius 2. So that would be the circle of radius 2 is just 2 cosine u plus 2. This should be sine u, not sine v. And then the v value is just letting my z go up and down. So my u should be between 0 and 2 pi, because that's the angles to give the circle. And then my z values go all the way from -3 to 3. And that gives me my entire cylinder here. So just like with curves, you'll get better with these the more practice you do. Make sure you understand how we got these 3 surfaces, and then you'll be ready for actually introducing flux integrals and how to actually do those integrals.